All right, now let's look at something we've looked at before in DC circuits, and that's the maximum power transfer theorem. So let's consider how that's going to work in AC circuits. So we remember the maximum power transfer theorem, just to quickly review it. As we saw before, given a Thevenin voltage and a Thevenin resistance, back when we were looking at this in just simple DC circuits with resistors, we saw that we could add a load resistor across the Thevenin equivalent of a circuit. And we saw that for maximum power transfer, RL had to be equal to RTH. So we got maximum power dissipated in the load when the load resistance was equal to the Thevenin resistance. So this is back when we were looking at DC circuits with resistors. Now let's consider the frequency domain. Let's say we have this circuit, where now we have a Thevenin impedance, a phasor voltage, Thevenin voltage, and now we want to know what value of load impedance results in maximum power transfer in this load. Now, looking at this, one would think that the kind of obvious and intuitive answer would be that ZL must equal to ZTH for maximum power in that impedance. It seems logical, it seems intuitive. It's also wrong. It does not equal ZTH. And there's another case of where your intuition can lead you astray. Let's now go and let's consider what maximum power transfer would be. And once again, we have to go back to some of our basic math. So now let's look at this and let's consider what is the required value of ZL to maximize power in that load. Okay, so in this case, I'm going to define a current flowing around this circuit. I'm going to call that I sub L. And I'm going to assume that ZTH is described by this. Let ZTH be equal to RTH plus J times XTH. So XTH indicates a reactance. This could be a positive or negative number. It could be an inductor or it could be a capacitor. We don't know. We don't really care. Let's let ZL be equal to RL plus JXL. So once again, a real component and an imaginary component that can be positive or negative. So given these definitions, we're also going to assume the following. We're going to assume that VTH is equal to some VTH magnitude at a phase angle of 0 degrees volts. Now I could make this theorem work with any value, but in this case I'm going to make it easy on myself. I'm going to pick a simple value with a 0 degrees phase angle, which means I will have simply VTH, just the magnitude of that phase angle, or the magnitude of this phasor in rectangular form. So given this, I can now write an equation for IL. IL is equal to VTH over ZTH plus ZL. Plug in all these values, and I will get VTH magnitude divided by RTH plus RL plus J times XTH plus XL. And so all I have here is I've grouped together the real terms and the imaginary terms when I added together those two impedances. Okay? So given this, I can now take the magnitude of this. The magnitude of IL will be equal to VTH divided by the square root of RTH plus RL squared plus XTH plus XL squared. And the reason I wanted the magnitude of the current is because I know that the real power is only going to be dissipated by the RL term in the load. And that power is going to be equal to that P load will be equal to the magnitude of IL squared divided by 2 times RL. So that is the power in the load. All right? And this will be equal to, when I plug this in, will be equal to 1/2 times VTH squared times RL divided by RTH plus RL squared plus XTH plus XL squared. And just to make this uniform, I'll call this P load as well, just to give it the same nomenclature. Okay? Okay. So here is my equation for the power in the load, which is strictly going to be a function of the real part of the load, R sub L. All right? Now, this is the equation that describes the power of the load, the average power, or the real power. Now, I know that I can't change VTH or ZTH, but I can adjust the values of RL and XL. I can adjust my load to try to maximize that real power. So what do I need to do? Well, in this case, I can vary two terms. I can vary either RL or XL, which means I'm going to do the same thing I did before when we looked at maximum power transfer. I'm going to take the derivative, the partial derivative with respect to RL, the partial derivative with respect to XL, and set both of those equal to 0 in order to find what my value needs to be. So let's do that. So given this, if we can vary RL and XL, then P load is maximized when the following is true. Partial derivative of the load with respect to RL is equal to 0, and when the partial derivative of P load with respect to XL is equal to 0. So I have to take two partial derivatives, set them both equal to 0. I have to satisfy both of those. So let's do that. Let's first take the partial, let's take this function, and let's first take the partial derivative with respect to XL. So if we do that, this will be equal to minus VTH squared times RL times XL plus XTH divided by RL plus RTH squared plus XL plus XTH squared, and then that entire term is squared. So I haven't bothered to go through and do all the steps of the derivative. I'm just assuming we can take that derivative, and I've just given you the result. And so given this answer, what we find is that we want to set this equal to 0, this term, and set it equal to 0. Well, what's the obvious way to set all of this term equal to 0? Well, if I set the numerator equal to 0, this becomes 0. And you know how I can do that? By setting xl plus xth equal to 0. So this is equal to 0 when xl plus xth is equal to 0, or xl is equal to minus xth. So that's the first part of my requirement. Now let's do our next part. Given this, let's plug it into this equation. This term disappears. So now I can rewrite P load. So in this case, P load is equal to 1/2 VTH squared times RL divided by RTH plus RL squared when XL is equal to minus XTH. Let's take the partial derivative of this. And so in this case, partial derivative of the load with respect to RL is now equal to 1/2 VTH squared divided by RTH plus RL squared plus -1 times VTH squared times RL divided by RTH plus RL cubed. And once again, we want to make that equal to 0. So what do we need to do? Well, if we combine terms, and I'm going to skip a couple of algebra steps, but if we combine terms in this equation, we'll get the following. We'll get 1/2 VTH squared times RTH minus RL divided by RTH plus RL cubed. So all I did was I multiplied top and bottom of this function by RTH plus RL and then just combined the numerators together to get this. And once again, this must be equal to 0. And in this case, how do I make this equal to 0? Once again, make the numerator equal to 0. Easiest way to do that is to make RTH minus RL equal 0. And therefore, RTH minus RL is equal to 0, or RL is equal to RTH. And therefore, ZL is equal to RTH minus J times XTH. The sign of the imaginary part changes, which in terms of complex numbers, when you take the imaginary part and flip the sign, you get the complex conjugate. So ZL is equal to the complex conjugate of ZTH. And this is the condition for maximum power. According to taking these derivatives and setting them equal to 0, that will maximize the power dissipation in RL. All right? So what this says is this, and this is kind of the way to look at it intuitively. ZL is equal to ZTH complex conjugate for P load max. In other words, if the Thevenin impedance is inductive, the load impedance must be capacitive and vice versa. In other words, what we want is we want the imaginary parts to cancel each other out. And that's exactly what we get. So if, for example, we had a problem like this, where we had this was 10 at a phase angle of 0 degrees, and this was 10 plus J10 ohms, and we had an inductor, what we want is a load impedance where we take the plus 10 and the minus 10 and we add them together, and they're going to cancel each other out. And in that case, all that's left will be the real parts when I look at the maximum power. So I effectively turn this back into a resistive circuit by making the load impedance equal to the complex conjugate of the Thevenin impedance. Okay? So in this case, what do we get? Let's do another calculation here. What is the actual power itself? What is P load max going to be? Well, as we already saw, P load must be equal to 1/2 VTH times RL over 2 times RL squared. If XTH is equal to minus XL and RTH is equal to RL. Or actually, I should say that the other way around. If XL is equal to minus XTH and RL is equal to RTH. So, if we make these substitutions, we get this for our P load. And what do you know? Very nicely, the RLs are going to cancel. So this is equal to 1/2 times VTH squared divided by 4 times RL, which will be equal to 1/8 times VTH squared divided by RL. And that is P load max. However, I typically tell people, don't use this formula. Don't try to memorize it. If I give you a problem like this, and I ask you, what is the power in this load? Using the maximum power transfer theorem. You know how to do that. Calculate the phasor current going around this, and then once you know the phasor current, you know the P load must be equal to the magnitude squared divided by 2 times 10. So I don't normally tell people to try to memorize because memorization fails you. But if you understand how to calculate complex power or real power in a circuit with a complex impedance, then in this case it's very easy. Use phasor analysis. Calculate either the voltage across the resistor or the current through it. Just use the formula. So don't rely on memorization. Rely on the fundamental concept, and you can always derive the answer very easily. Okay? All right. So this gives us the background we need now to go through and now solve for maximum power transfer in AC circuits, which really that's why we never looked at this when we looked at Thevenin and Norton impedance. We didn't have an understanding or definition for power, but now we do. So now this kind of fits in the last bit. So next time we'll look at one other interesting little definition, and that's a definition of RMS voltages and currents. If you think about it, you notice there's something that keeps creeping in, and you'll see that, for example, power in a resistor is V squared over 2R, or equal to I squared over 2 times R. You know, this looks very much like DC power in a resistor, except for that 1/2 term. Wouldn't it be nice if we could get rid of that 1/2 term? Well, with the definition of RMS voltages and currents, we'll be able to do exactly that. We'll look at that next time.